to explore the energy storage capabilities of using composite materials in space applications. A sponsored candidate from Liquid Propulsion System Center, ISRO. He has been working in the mechanical design and analysis team for the last 10 years and has primarily contributed towards metallic pressure vessel and structure for the cryogenic stages of ISRO CUS C25 and SC120. His work has involved design, analysis, and some aspects of testing, both on material and structural levels.
No, his regular.
Good afternoon, everyone. So I'm Abhishekaran.
It's a nice question you asked, Jairaj.
No, because that is something that we deal with, and
Right.
the bridge that we always try to bridge between testing and simulations.
Right. So in the same program, she's also involved. The certification, trying to use simulation for certification.
But I'm not quite sure. Have we completely eliminated the?
No.
It's,
No. The tests are still there. Otherwise, I would not fly.
So, yeah. So I've just recently joined Masters here. I'm doing my first year. So this is completely in its preliminary stage. We just conceptualized what probably I would be looking at. So I'll just go through, my ideas on it, and this I request it to be a completely interactive session. So kindly, hit me with any suggestions or any questions or criticisms of the topic. So that's not connected.
Slideshow. Yeah, I think slideshow.
Yeah, the point is, yeah.
So I've just broken the talk into like 6 portions. One is just the introduction of what I'm talking about or what I'm planning to do in this topic. The other is the structural batteries. What do they really mean?
It's not visible.
Yeah.
So is it visible right now?
Yes, sir. Visible.
So like I was mentioning, I'll break it down into 6 parts. It's a very short presentation. So I hope I take up the time that's being given to me. The second part is just an overview of what are structural batteries, or what are the current structural batteries that are there. Because there are 2 categories to it, I'll just come to that. The other one is what is the state of the art, what is going on, what are the properties that we have achieved at present at a lab level, and what could be a probable commercial level. Then I'll come down to the space applications. Till date in the space missions, especially the exploration missions, what are the kind of energy storage and generation that have been used? I'll probably talking about the NASA missions to Mars, mostly about those. And then the proposal that I am bringing in is to actually bring in an additional functionality, structural battery, which is to introduce an energy generation mechanism into it. And the future directions, which is basically going to talk on what I would like to work on, or the questions that I'm asking, what I will be addressing probably in the coming 1 year of my MTech here. So this is the introduction where these are the objectives that I set for myself into looking at it. One is to see how can we make it feasible, because right now most of the structural batteries are at a lab level, and they are primarily being focused on automotive or something like a phone electronic kind of an application. So when we bring it into a space kind of an application, what are the changes? What are the kind of properties that we look at rather than what we look at on the Earth? The other one is to have a mathematical model, though they do exist, but probably for myself to delve into it and see if I can bring in something into it, to kind of get a bulk properties of these composites, like based on how we kind of layer them, or different kind of orientations of different layers, what are the bulk properties that come. And the other one is to have a design methodology. For example, for a given mission, like different missions will have different kinds of approaches or the different kind of properties I want. Can I develop a design methodology which can be utilized to develop a certain composite for a certain mission? Like there will be a certain requirement. How do I work about it? Can I have a systematic approach to it? And the last part is to actually introduce an additional functionality of energy generation. So this is what I'm talking about. Like, we try to bridge three functionalities. One is the structural property, the storage properties, and the energy generation properties. And energy generation, I'm primarily looking at a photovoltaic kind of an approach, wherein maybe a top layer of the composite will have a photovoltaic cell, which will again be bridged into the battery cell. So the energy can just be stored into it. What are the motivations? Especially looking at a space application, we'd like to reduce the volume, because when we make a rover or an orbiter of any of that sort, we'd like to keep a smallest volume footprint for it. Otherwise, it becomes hard to carry. The diameter of the launch vehicle will become larger. We'd like to reduce the weight. Obviously, when it comes to launch vehicles or any kind of a space mission, the payload weight is a very critical aspect, because when we go into space, the weight becomes exponentially proportional to the weight of the launch vehicle. I mean, the weight of the payload. And obviously, to improve the specific properties, which is again dependent on both volume and weight. So this overall leads to a reduction in cost, the feasibility of missions, because a lot of missions, we reduce the payload because the weight is not a feasible number, and improve the performance, obviously. So when we come to structural batteries, there are actually two kinds. One is basically what we know, what Tesla kind of uses, where there's a core structure, which is a casing, where the load transfer happens, inside which they have a series of battery packs. So it looks something like this. So you can see these battery packs are like a series of lithium ion cells, and they are put into a core frame structure. So this is a structure which is actually a load transferring member and a battery energy storage one. And the other one that we're looking at is what we call the structural battery composites. This is a completely material kind of a property. So the material in itself has the ability to store energy and carry load. So there are a lot of types, but there are two main types that we are looking at. One is a laminate kind of a layer thing, where there's a carbon fiber layer on which a graphite layer is applied, and there's a separator, and the anode is a carbon fiber with lithium ion and phosphate layer on it. The other one is a fibrous kind of an orientation, where there's a central core around which there's an electrolyte, which is a solid electrolyte, around which there's a copper foil, and obviously an outer shell, which is a primary load taking member. So if we start looking at what is happening, right, it is actually, especially when we look at an automotive or an electronic industry, it is primarily focused on increasing the energy density and reducing the cost, and also the environmental impact. But when we kind of go into space applications, one of the more critical aspects is the stability and how it reacts to the temperature variations that are around it. Especially if we look at Mars, we're looking at temperature variations at the extremes from -80 to around 90 degrees centigrade. And especially lithium-ion batteries, they do not work well, under -20 degrees centigrade. But if we look at what is being done right now, NASA has, if we compare the Tesla's energy density, it is around 300 watt-hour per kilogram. And NASA has recently at a lab level developed something that gives 500 watt-hour per kilogram. But this battery does not work less than 20 degrees, -20 degrees centigrade. So if we look at how the research has been progressing, these are the kind of metals and the different polymer electrolyte materials that are being used. And you can see that mostly it is being focused on energy density, reducing the benignity of the environment, and the safety aspects of it. And also recently, the QuantumScape has developed a new kind of solid state battery, where they talk about where the anode material itself is lithium. So basically the way it works is when it's completely charged, the lithium ion deposits on the anode and it creates like, an anode material there. So this, they are claiming that, it gives a very high energy density that is not possible in the current lithium ion batteries. Now, when we come into what we require from a structural batteries, it includes the mechanical properties, the safety properties, and all these. So these are the basic applications where this can be applied to. And we are mainly looking at the mechanical properties and the electrochemical properties, which mean the energy density, the volume density, and the mechanical properties like the modulus, the strength, and flexural rigidity. So this is the current research that is going on at the lab level and the kind of properties that we have achieved. If you can see the best that we have here, this best specific energy is 205. And for that set of material, we have an elasticity modulus of only 3 GPa. And the fractional modulus for that material is only 12.9 GPa. If we compare it with even with aluminum, the elasticity modulus of aluminum is 71. So it's like way lesser. And if we look at something that is on a structurally what is usable, in fact, this is developed by KTH, and this is at a stage where it can be used commercially also. We get a specific energy density of only 23.6 with the elasticity modulus of 25. So just to give a reference, lithium ion batteries used for space generally have a energy density between 200 to 250, and obviously, the casing for them is made of titanium, so that is around 110 GPa. So just by looking at it, we can clearly say that we are still not at a stage where they are having the properties which can completely be used. So we'll just talk about the space missions and the kind of energy storage that have been used. So, like in a space mission, a non-human space mission, so we generally have mainly two kinds of payloads. One would be the orbiter, which orbits around the planet, and the other is the lander or rover, which explores the planet. So generally in an orbiter, we would use a solar energy generator because that is more convenient, and also like, we don't have to carry a radioisotope. But sometimes for landers, especially recently, we are using a radioisotope generator, which is called the RTG or MMRTG generator. So what are the necessary properties that we require? One is, like I said, high strength, high toughness. The density has to be low, basically implying that the specific properties have to be high. And the property retention should be quite resilient under wider temperature ranges. And also a long lifetime, because there's no intervention that can be had for its whole life. It has to completely operate without any intervention for that particular lifetime. And obviously that goes down to stability and all that. So we'll just look at one of the missions. One of the first missions which landed a rover on the Mars planet is the Viking 1 and 2. This is the orbiter of it, but the rover used a nickel cadmium battery with an RTG generator for its power source. The first use of lithium ion was in the Proba 1, which was by ESA. Coincidentally, this was launched by ISRO. The launch vehicle was PSLV, and this was the first use of lithium ion. Also, just to bring in it nearly takes a decade. Like lithium ion was commercially brought into the picture in 1991, but it nearly took us 10 years to bring it into a space environment. So that's the kind of time it takes probably to have something that is set up on a lab, especially when it is evolved for a different applications, to then scale it down to a space kind of an application. And then the first use of lithium ion with solar cell was done in the Spirit and Opportunity. So here we had a solar cell which would power the lithium ion. The solar cell provides the energy in the daytime region, and the cell provides the peak energy, and sometimes in the night region when it has to operate. And the next one is which is currently being used by NASA. This is the kind of combination. They use a lithium ion battery with an MMRTG power generator. It's actually a radioisotope thermionic generator. There's a radioisotope which generates power by using a thermal energy. So, like, something. Okay. Yeah. So basically, when we add these two properties, it becomes a structural battery composites, like, the battery and this. And we would like to also bring in the energy aspects into it, energy generation aspect into it, because if we look at these missions, they have had a completely different structural element just to carry the battery or the energy generating element into it. So why not we bring everything together and then make it more efficient that way? This is the question that we are looking at. So, so like I mentioned there, this is the comparison of how the energy density and the modulus of elasticity is for the general materials versus the structural battery composites that can be gotten at a commercial level right now. We can see that obviously it is much lesser than what we require, right? And this is just to give the values of the kind of mass and the volume that that we need just to carry an energy generating and a storage source. This is the Perseverance rover, which is currently on Mars. So this has two lithium-ion batteries, and it has a MMRTG generator, 110 watts. You can see the volume is nearly, it has the envelope of the power generating system, which is the blue highlighted one. Yeah. That's it. So the blue highlighted module is the power generator. You can see it's actually a significantly large portion of the volume, and it's nearly 640 mm dia and 660 mm length, and it is around 50 kg. Mass wise, it's actually a little less because the energy generator is just a 5 kilogram radioisotope. Generally, if it's a different kind of energy generator, it will be much larger. Obviously, the radioisotope is a much efficient way of generating power. But nevertheless, you can see that the volume is actually much larger. So why don't we just replace this? That's the question we're asking. Also, especially when we go into a structural battery, we can replace the complete body of the battery. So that would make far more, like mass saving. But like I mentioned, like, properties are much lower. Would it really be relevant to pursue? I mean, are there numbers that justify, pursuing something like this? So there was a study that actually tried to change the Tesla Model S by replacing the non-load taking structures by putting a structural battery like the doors and the other parts of it. And they theoretically showed that the range of the Tesla Model S can be improved by nearly 23% if such an experiment can be carried out. So, like, based on the information that, like I talked about, and so these are the questions that I asked. One is, can I really integrate a solar cell into a structural composite? Does it make sense? Because especially a solar cell is going to be a very brittle, low strength materials. And if I put it, and it always has to be on the top layer of a composite. And if it undergoes bending loads, it will take most of the tensile strain. Even if not the stress, it will take the strain. So would it be feasible? Can I really form, maybe I can add it into a grid-like structure so that the strain is distributed in between the grids, something. Can I have something like that and integrate it into this? And obviously, how does the addition of it affect the properties? Because we need to have a mathematical model for this. So developing a mathematical model so that we can understand these things. And like I mentioned, what is the optimum configuration? Like, how can the solar cell be distributed? Do I add reinforcement in between? Do I break it down? Do I add strain taking regions in between? And the other aspect that I actually did not talk about is most of these missions have their electronics operating in a very set temperatures, that is like minus 40 to 40 degrees centigrade. And the radioisotope actually generates the heat, and there's a heat distribution circuit that actually keeps the temperature in control of all these critical electronic components. So in this case, if we actually eliminate such a system from it, can I have a way to actually take the heat generated in the battery and dissipate it into the system so that that makes it possible, that makes the design environment feasible for such a mission? And can we have an optimization algorithm so that given a certain properties, and I just plug it in and I get what kind of a configuration is feasible for a mission? and obviously an experimental validation of the theoretical. Yeah, thank you. Any questions, any suggestions for how to go further in this?
Sure.
Yeah.
Yeah, thank you for the presentation. I don't know much about the batteries from the academic point of view, but I do have an off-grid home with solar panels and batteries. So I have a question about that. You were suggesting adding the solar generation to the battery itself,
Yeah.
right? But then the generation of energy is very sensitive to the angle of the sun. So you would have to tilt or to orient everything. So it would be the battery and the solar panel towards the sun, towards the source. How would you couple that with being a structural panel?
Yeah, that is true. So actually, especially when I talk about integrating the solar panel, I'm primarily thinking about it from a space habitat kind of a perspective. So there was a paper which talks about how, in case we're having a space habitat mainly powered with solar energy, how would we work around it? So what they say is, because solar cells are, Mars has a very high wind. It has a very high wind velocity. So these solar panels need to have a very high mass attached to them so that they don't fly away when the wind comes.
Okay.
So what they're proposing is to have Kevlar reinforcement between different solar panels, and they tie out these heavy mass. They just tie rocks from it. So that prevents it from happening. But in this case, you don't have to have such a secondary structural element. You can just have one. And the panel itself, because your composite has a certain structural strength, it can take that weight and it won't fly away. So that is primarily from there, because obviously for the rover, it does not make sense because the rover has a much smaller surface area. So it needs to have something that extends further. But in an orbiter environment, it makes sense because an orbiter will have these wings kind of a thing. If you look at Juno and missions to Jupiter, that nearly has a 20-meter span. It's a 20-meter span with a very small central mass, and it has extensions to it. So mainly for those, solar makes sense. But in an orbiter, I still think this is just a secondary energy generation. The primary has to be a radioisotope or something.
Definitely a topic of interest, I think. Nowadays, more and more.
I mean, again, like it's very preliminary. There's hardly any results for me to show. It's just
I know you've been working on it just for a few weeks now. So
Yeah.
and I was quite impressed within a few weeks that we could put a story together. Because this is the way we generate a problem definition. You're not at there the problem definition, but at least in terms of doing the literature survey and looking at the current state of the art and summarizing it and seeing the different directions in which it could go to. And then probably we'll try to decide for a problem definition, which is befitting and you're capable to solve.
One query. Why do the casing of the battery need to be high strength and high fatigue resistant? What is the necessity?
no, like I mean, especially when you go to a rover scene in a in an environment like Mars or Moon or anything, there is actually a lot of vibrations that come. So inherently, all your structures have to be fatigue resistant. But out here, the RTG is actually a radioisotope, so it requires a lot of shielding. So that is one of the main reasons why the structure around it is bulky and there's a lot of. It has to have thickness
Oh, yes.
because the radiation reduction comes from the thickness only. So that's the main reason why it looks so big. I mean, like even though
Because of the internal pressure of the battery.
no, it's a simple radioisotope. There's like a plutonium, I think it's a plutonium dioxide, and that radiates energy. So that is taken and it's converted into heat, and that's how you generate energy from it. But this radiation is not. I mean, it's not a good thing for the other component. So it has to be shielded.
Yeah.
So that's the main reason. The fatigue is like inherent.
Yeah,
It's inherent for everything.
High strength is what
So high strength, I mean, simply comes from, I mean, you have high strength, you can reduce the mass, right? I mean, high strength is basically in terms of its specific properties. I would rather say it should have high specific strength. So you reduce the thickness and again, directly go down to reducing the mass of it. So any more questions or suggestions? Thank you, everyone.